Hi, I'm Francis, and today we're talking about the Mallat Scattering Transformation for reduced order modeling of partial differential equations. So first, in this talk, we'll essentially be using the MST as a physically principled autoencoder to propagate the dynamics of PDEs. So we can do this. This is grounded in several different ways. So the first reason is that the MST acts as a deep convolutional network with predetermined weights. These weights have a physical basis, which reduces the search space required to surrogate the dynamics. Also, in terms of physics, when to kinetic theory, it's constructed as a modified linear Weyl transformation that is manifold safe, and through the BBGKY hierarchy, it yields the generalized master equation. Also, in field theory, the MST gives you the S matrix up to the LZ prefactor, which is essentially the generalized Kreutz function of the field theory in a scale-dependent basis. And finally, it also describes the topology of the manifold by yielding the scale-dependent topological indices that describe the cohomology of the dynamical manifold. So next I'll go into a little more detail about the topology details of the MST. So you can reconsider either field equations, statistical systems, or data simulation problems as problems that only depend on geometry. But in this case, you have the complication that the curvature is field-dependent, or it might be dealing with non-Riemannian manifolds. So to quantify this, you can define an effective action in the field, as in the field equation case, as this function of the partition function. And it can solve for the path of least action, which is S naught of the path, and by taking the functional derivative set it equal to 0, which gives you the optimal path in this thick line here. So in addition to this path of least action, you can also define some area where the action is relatively small, order of 1, based on the inverse mass or second order coefficients of the MST. And I'll go into more detail about the MST itself in later slides. But essentially, what this does is that it gives you the integrated curvature or topological index of the manifolds, which gives you crucial topological information about the dynamics. So next, I'll talk about how the MST relates to the generalized master equation through the manifold safe Wigner-Weyl transformation. So the Wigner-Weyl transformation in general takes operators either to or from a phase space, but in this purpose, we actually modify the transformation so it's a correct commutator and is manifold safe. So in order to do that, we define the local Fourier kernel as the mother wavelet at the MST, and actually enforce a partition of unity, which is a father wavelet to the system. So from this, we can actually identify the first and second order MST coefficients. In this case, the mother wavelet acts as a convolution filter if we're going to have an analog to a CNN. The father wavelet acts as a pooling operator to aggregate the outputs. And we use absolute value function to act as activation function on our activation values. So using this, I'll next describe how we can view the MST as a transformation into the sparse Kuban basis. So using the BBGKY hierarchy and the ideas of Bogolubov, we use the generalized master equation to propagate the dynamics in the Kuban basis, which is both sparse and linear. So to satisfy detailed balance, where the dynamics exiting one state is equal to the dynamics entering another state, we actually construct the matrix so that the integral of the time derivatives of the dynamics are equal to 0 over scale. And in order to do this, we identify the upper diagonal a priori from MST by taking the second order coefficients and squaring them divided by first order coefficient squared. And then we define lower diagonal as a rescaling of this by the energy. And then we also define diagonal as a negative sum of the vertical columns. So by doing this, we obtain a k sub p prime, or in later sets also for this is k sub kk prime, which is propagated that defines the dynamics. And I'll describe that in more detail on the next slide as well. So we can optimize these coefficients to find k sub p prime, where we can find these from the MST directly. So I'll just quickly go over the different ways we can find them. So you can be found from direct normalization of the MST transformation. You can find the upper diagonal of the K matrix from the MST by dividing second order and first order coefficients. And also need to find the energy. So you can also either find this from the data, taking the largest of the fluctuations, or you can optimize it separately as well to find the energy scaling factor. And then you can decompose this matrix to obtain the eigenvalues of the system. And this gives you the manifold that converges to long times. And interestingly, if we assume this is linear, what we can do is that we can propagate this analytically using this solution here of e to the sigma sub PET. This allows us to bypass some limitations of finite differencing, such as the need to adhere to the CFL condition. So we can just propagate this analytically and have it be stable. And looking more at the null space that it converges to, what we have is that this is sparse due to normalization equations with RGEs from field theory. And I'll go through why these guarantees are present in more detail next slide. So we're looking at the RGEs. We can find that the dimension of the subspace is given by this expression, as a probability density function is given as some function of k to the beta I sub k. And the number of I components is equal to the number of coupling constants plus the number of fields. This parameterizes the codere dimensions of the dynamical manifolds, and it gives you essentially the dimension of the subspace. So in general, the dynamics will converge to a subspace that solves the normalization equations. This is a quick example. We can apply the RGEs to 5 to the 4 field theory and quickly solve them as ODEs. And in this case, you'll get a solution that depends on 3 variables. We have phi, which is the fields, the mass m and gamma. And these individual betas act as unit vector of the subspace, so we can parameterize the subspace in 3 dimensions by selecting beta I and log k. And this defines the latent space of our model. So moving towards the moving more towards autoencoder model of MST. So what we can do is that we can define transition kernel, which is the generator of the infinitesimal time derivative on the variable u. So we're defining this as a functional of x. And it can be used to advance the variable u. So if we take h as MST, as this latent space operator as the MST, what it first does is it translates the dynamical variable into the latent space by applying h of u, its functional operation, and applies the k sub kk prime propagator to this latent space. Then it's broadcasted back into the full space by this h inverse operator here. And what this gives you is that it gives you the time differential of the dynamics at some instant in time. So we can use this to propagate by plugging this back into this function here and solve for how u changes the function of time here. And if we go through this diagram here, in some more detail using MST specifically, so we take in our data x, and then by applying to MST, we get a range of coefficients at different orders. So F1, F2, F3, F4, and F5, and so forth at different respective orders. What we actually can do here is we can truncate this hierarchy at F3 equals 0. So any order is higher than F3, so F4 and F5 won't be set to 0. And this actually does something interesting here. So by doing this, F3 would normally set the rate of F2, and F2 would set the rate of F1. But since F3 is identically 0, the F2 is constant in time. So this means that we have a constant propagator that we can use to propagate the dynamics of F1, and we can just use that to see how F1 changes in time. So after applying this propagator k, which is based on F2 divided by F1, we can actually extract the time derivative of x by applying the inverse MST to this value here. And this acts as the function transformation. It's a Cuban basis where k sub kk prime is linear in this scenario. So applying this to some simple systems, just the Burger's equation and the diffusion equation, what we can see is that the initial conditions and the dynamics affect the MST equation in different ways. So the MST is largely invariant to choice of initial condition. So by choosing different widths of the Gaussian, you can see that the rate coefficients are largely similar. But for instance, the Reynolds numbers affects this more strongly. This is due to the fact that Reynolds numbers actually changes the dynamics and how they that translates through space and time. But the initial condition should not change the dynamics over time. And this as well, especially with the different equation choices, where there's more peaks in this area of the rate coefficients for the Burger's equation as opposed to the diffusion equation in this case. So by comparing these two cases, we've run some cases where the coefficients are optimized directly from the data and where they're obtained by the MST entirely. We can see that we can actually extract these coefficients with much less optimization by using the MST. So in both of these cases, both of these fit cases from the MST space, as well as the a priori defined MST cases, we're definitely in a much smaller search space than a traditional convolutional neural network, which has thousands or millions of parameters to propagate dynamics. Or in this case, we only have like at most a few hundred to optimize. In this case, we can see that for the MST coefficient to obtain a priori, we are able to obtain much more detail in these small scale coefficients that is very hard to actually optimize by fitting these coefficients directly. And we see that for these coefficients as well, coefficients are also fairly similar in structure to the MST dynamics, which is also a promising sign. So finally, by looking at the Generalized Master Equation, you can see that we reproduce the dynamics very well by using the fit coefficients. So you can see that it's almost an entirely overlapping cases between the propagated MST coefficients, both the f1 squared cases, the log of f1 squared is plotted in the middle, as well as the time differential f1 squared. So it's very good agreement here. The one caveat being small scale coefficients are a little harder to optimize than the large scale coefficients. So in conclusion, we have that the MST acts as autoencoder that's principled via physics, as we've shown earlier. It exposes the dynamics, the representation is optimally sparse with no constraints on the manifolds. And finally, it optimally approximates the attractive manifolds or latent space in a very low dimensional subspace, which is optimal representation in this case. So thank you for your time. Are there any questions?